Hi everyone, my name is Daniel and I'm here today together with Sam and Zeke. This talk is all about the important role that Rust played in launching secure messaging, the Guardian's new anonymous whistleblowing system. And this is also pretty exciting for us because we're now finally able to talk about it after we spent the last 3 years silently developing it. And we're sorry that we can only join you digitally today, but we'll be available in the conference Discord afterwards for any questions that you might have and for continuing the conversation. So our talk is roughly divided in 2 parts. So I'll start by introducing the system, why we built it and how it works. And after that, Sam and Zeke will dive into some of the specific aspects of Rust that were particularly helpful for us and critical for shipping secure messaging. So imagine you just cover something going seriously wrong. For instance, at your workplace or within an organization. You've tried to fix it, you've used the internal channels, but nothing has worked. So you might consider reaching out to an investigative journalist as a source. But how would you actually do that? This is what we call the initial contact problem. How a source can securely reach out to a journalist for the very first time. And we know this is a very difficult problem. For instance, you'll want to avoid leaving a digital footprint right from the very beginning because downgrading security later is always possible, but upgrading it retrospectively, that's quite tricky. And once there is any metadata linking a source to a journalist, that link cannot be undone. One solution often suggested is using anonymity networks like Tor. However, if you're the only one in your organization using Tor, that can paradoxically actually make you stand out. And at the same time, these tools can be difficult to use for those who aren't so tech savvy. Whistleblowers have been essential for some of the biggest stories reported over the last few years at news organizations like The Guardian. This includes the Snowden revelations, the Panama Papers, and the Uber files. And the first one is particularly interesting for us since the initial contact by encrypted mail proved difficult, and that led to significant delays. And these are all reasons why The Guardian has built secure messaging. It's an easy-to-use, secure, anonymous mechanism for whistleblowing built right into the mobile app. And our system uses what's called cover traffic. So all installations of the app periodically send cover messages to our servers, which create some sort of metadata noise amongst which real messages can hide. And importantly, by leveraging the large install base that the app already has, we have a large anonymity set right from the start. And therefore, secure messaging can provide strong plausible deniability for sources and whistleblowers. And I brought you some screenshots to show you how this would look like for a source. So a user can navigate to secure messaging either via the app menu or specific callouts and articles. And we learned from user studies that in-app help pages are super important. So we've included an extensive help section and an onboarding screen. This also means that the user doesn't have to leave the app and risk creating an online search history when they, for instance, have to Google for an answer. All local data is always saved in an encrypted vault, and for this, the user has to remember a 3-word passphrase that's additionally protected by the device's secure element. The interactions with the journalist ideally feel like a normal end-to-end encrypted messenger, like Signal. However, there will be a slight delay before a message is actually sent, and you might spot that on the third screenshot that one of the messages is actually marked as pending. And this is intentional, as outgoing messages from a source replace scheduled cover messages, and so they must simply wait for the time slot. So how did we get here? Well, it was quite the journey. So this all started even before 2020 as a research project at the University of Cambridge involving a research team including Mansoor, Diana, Alistair, Ross, and myself. Back then, this was called Coverdrop, and we still use that name when referencing the underlying technology today. It started with workshops with investigative journalists and engineers from news organizations. And the idea was to really understand what are the biggest problems that they faced and what are the constraints that a solution would have to work within. So rather than choosing the approach, solution looking for a problem, which arguably happens way too often in academia, we really started by trying to understand the problem first. And the output of that, which was the original cover paper, got presented at the Privacy Enhancing Technology Symposium in 22. And afterwards, we got a message from the folks at The Guardian asking whether we'd be interested in actually building it. And I mean, we already had the protocol implemented in a few hundred lines of Python, so how hard could it be? Well, it turned out that taking an academic prototype and turning that into production-grade software is quite the undertaking. And overall, it took a team of developers 3 years until we finally launched in June this year. And was it worth the effort? That has been a nagging question at the back of our minds for the entire time. But luckily, we've all been generally encouraged by both the volume and the quality of the messages that we've been received during the last weeks. Let's go back to the more technical side of things. Let me show you a simplified diagram of how the system works. So you see the users that send cover messages throughout the day, and then there is the cover node, which is a service that lives on premises inside the Guardian building. It is also the only component with access to a special secret key that allows it to remove the outer layer of encryption, allowing it then to distinguish between cover and real messages. And that means also that the inner messages between the source and the journalist remains end-to-end encrypted, so there are 2 layers of encryption. The cover node then discards the cover messages and collects the real ones, and when it has collected sufficiently many real messages, it publishes a fixed size dead drop via an API service. Journalists download these dead drops and then try to decrypt all messages in there, and those they can successfully decrypt are meant for them, and they can show them to the journalist. At this point, you might be wondering what all of this has to do with Rust. Well, components like the cover node are super critical for the security of the entire system, as it, for instance, guarantees the anonymity of the sources. So we needed to write it in a way that never violates its core security constraints, while still ensuring that it can handle a high throughput of messages. And that's where we found Rust to be a particularly good fit for the job. These are some of the topics that we'll cover today in our talk. So Sam will start by explaining how we use the type system to guarantee the safety of these critical components and build misuse-resistant APIs. And secure messaging is also different to other systems, as we simply cannot look into production services. That would violate its privacy properties. So Zeke will talk about our approach to testing and how we keep some level of observability using Rust. And finally, we'll touch on how Rust's performance characteristics made it easier for us to adopt secure design patterns without overwhelming new developers joining the team. In the end, I would say it's all about making sure that we can still sleep well at night while working on such a sensitive system. And Rust really delivers here when used correctly. If it compiles, that generally means it works correctly, which in turn gives me the comfort that allows me to sleep well at night. So just before we dive into the details, let me quickly walk you through the full architecture, as this will be important later. So as mentioned, the users send these cover messages, which actually then go by a CDN to an appender microservice, which adds them to a message queue. We use AWS Kinesis as our message queue. And the cover node then polls from that stream, ensuring that The on-premises servers actually don't need any incoming connections, which gives them additional security properties. And from there, it prepares these dead drops and publishes them to an API service, which uses a database to persist them. And then the journalists can talk to the API service and get their copies of the dead drops and then try to find messages in there by trial decryption. The reply messages from journalists to sources work in a similar way, traveling by the API to the Kinesis stream to the cover node back to the user. There are some additional services that we haven't touched on yet. There is, for instance, another on-premises service, the identity service, which is also security critical as it facilitates key rotation and signing of the hierarchy of keys. The most sensitive keys, however, are kept on an air-gapped machine. So that's a laptop we keep securely in the safe, and it's only accessed for special ceremonies. And finally, where we can safely do so, we collect logs and metrics to help us understand that the system is running correctly. So where's Rust? It is basically in every component that we've written. And this also allows us to move a lot of the code into like a shared crate that later allows these services to easily talk to each other because they understand the same types, the same serialization, the same API patterns. And that has been extremely helpful to just have everything Rust in the backend. All right, with those introductory bits out of the way, I'll hand over to Sam, who will now dive right into the Rust aspects of implementation.
Thanks, Daniel. I'm Sam Cutler, and I was the engineering lead on the secure messaging project at The Guardian. Just to get everyone oriented, I'm going to summarize our approach to Rust before diving into some of the more advanced techniques we used specific to our security-conscious project. The majority of our services are HTTP APIs. We use asynchronous Rust throughout, Axon for handling web requests, primarily JSON payloads, Anyhow for error handling, and SQLX for speaking to the database, which is usually a SQLite database using the SQL Cipher extension to provide encryption. These are the basic building blocks, but you might be wondering how we structure the code to work well with the specific team we had at The Guardian. With Rust, you have the option to go for the most sophisticated, blazingly fast code, utilizing lock-free data structures at every level of your program, and minimizing allocations wherever possible. Or you can offer something like easy mode Rust, which I first heard articulated by Andrei Burgos at the 2024 Rust Nation conference. Easy mode Rust focuses on writing your code in such a way that it minimizes a lot of the complexities that are specific to Rust, allowing engineers who are less familiar with Rust to contribute more quickly. Given that we were the first team at The Guardian to adopt Rust, we had to be careful how advanced we chose to go. In the end, we tried to land on a tasteful combination of both the extremes. This would allow newer engineers to get up to speed as smoothly as possible, while also allowing us to keep the performance and security advantages that Rust provides. In practice, this means instead of structs containing references to other objects, we prefer our structs to have owned types. This minimizes borrow checker headaches. Instead of lock-free data structures, we prefer to wrap a read-write lock with an arc whenever we can get away with it, which is most of the time. You can have both great performance and approachable code, and at the end of the day, you can always refactor your code if you need the more advanced option later on. If you're a Rust enthusiast at your company and you want to bring others along, adopting a tasteful balance of these two approaches could help get other engineers and reach out to them where they are right now. So that's great and everything, but what can you do to improve our misuse resistance? We want new engineers to be able to join the project and get up to speed while minimizing the risk of them introducing new security vulnerabilities. The answer is, of course, using the type system. Rust has an incredibly powerful type system that allows us to express constraints on our code and have them checked at compile time. I'm going to start with the most basic pattern we use, the new type pattern. Our protocol requires that all of our app users constantly sending messages from their phone to our system. Usually these messages are fake cover messages, but if a source wishes to share some information, this cover message is swapped out for a real one. All of these messages can potentially be observed by adversaries while they're going over the network, so it's important that real and cover messages are indistinguishable. We achieve this through encryption so that contents cannot be seen, and padding so that all messages are the same size. But before any of our security features are applied, we use compression. This allows users to provide more information in a smaller packet, minimizing network usage, which is especially important in locations where network usage is more expensive. We then pad this message to a fixed size. This is so that the length of the message does not give anything away to our network adversary. Finally, the message is encrypted, using the cryptographic primitives I'll talk about shortly. This is a representation of the structure that handles everything except the encryption. We call it the padded compressed string. Since this data is compressed, it's not meaningfully UTF-8, so we represent the data with a heap allocated vector of bytes. We use a vector rather than a fixed length array because it works well with our compression and padding libraries, which simplifies construction. This vector is checked against the constant size which we provided at compile time. If the vector is too long after compression, we get an error. This is because our constraints have been violated and an adversary could possibly tell a real message was being sent. The new type pattern allows us to apply extra constraints to an existing type, in this case a vector of bytes, and also allows us to give it a nice name. That's great, but what about the cryptography? This diagram represents our entire key hierarchy. Each key is signed by the key above it, providing a chain of trust all the way to a trust anchor. At the top we have our organization key. This is the most important key which is used to infer trust for the entire rest of the hierarchy. Given its sensitivity and long lifetime, the secret part of the organization key is only ever used in an air-gapped sandbox. The next layer are our provisioning keys. These keys can be used to create more cover node services and journalists. If an attacker was ever able to spoof a valid provisioning key, they would be able to create a fake journalist account and potentially trick users into sending them their secret messages. As such, these keys are either kept in an offline air-gapped machine or on a well-defended on-premises identity API. If a leak were to happen, we do have additional checks and monitoring that would detect unexpected new journalists and would alert the team. Next, we have the cover node and journalist identity keys. These are used whenever an entity must prove its identity. For example, when a cover node publishes a batch of messages, or when a journalist wishes to update their profile information. This key prevents other actors from performing actions on their behalf. These keys are stored in an encrypted database that only the appropriate journalist or cover node has access to. Finally, we have our messaging keys. These are the keys that are used to encrypt messages and other content defined by a protocol. These keys are short-lived, and much like the identity keys, the secrets are only ever stored within the encrypted database that a specific individual or service can access. We primarily use the curve 25519 family of elliptic curve functions, that's x25519 for encryption key agreement and edit 25519 for signatures. We use a combination of the curve 25519 dialect crate and a wrapper around libsodium, which is a popular and widely deployed cryptographic library. We chose libsodium because we need to deploy our cryptographic primitives across iOS and Android in addition to our Linux servers, and libsodium is well tested and has already been wrapped for all of our required languages. Now that I've covered the basics of our cryptographic key hierarchy, we can discuss how we use Rust-type systems to improve misuse resistance. Two important parts of dealing with cryptographic primitives is having a strong understanding of whose keys are being used, which we call the role of the key, and verifying the keys are trusted before using them, which we call verification. To implement these checks on the roles and verification status on our keys, we use a type state pattern. The type state pattern can be summarized as using types to represent the state of your program. Cliff Biffle has an excellent blog post which includes 3 things to look out for when you want to apply the typeset pattern, which I'll summarize now. 1. Operations on an object only exists when it's in the appropriate state. 2. States are encoded into types. Attempts to use these operations in the wrong state will fail to compile. And 3. Types are functions that allow them transition to other states, adding and removing certain functionality. The first type state we have is a simple marker trait, which is our role trait. Different keys have different roles, which infer different capabilities and lifetimes. We want to prevent developers from accidentally using the wrong key for any given operation. We use a define role macro to quickly stamp out all of these roles, but the macro we use in our actual codebase is a little bit more complicated than the one shown here. Here is an example of how this marker trait helps. We have a function, createJournalist, which takes a name for a journalist, some other parameters, and a key which signs the journalist's initial identity keys, proving that the journalist is valid within our hierarchy. In this top example, our admin tool has attempted to pass in a signing key pair, which is the cover node provisioning role. So this will not compile, since the journalist function requires a journalist provisioning key pair, which is demonstrated in the second example. Next is verification. Remember that we don't want keys that have not been verified as trustworthy to be used for cryptographic operations, and we want this to be enforced at compile time. Not verifying your keys is unfortunately quite a common mistake in security-conscious systems, and we want to use the type system to eliminate this risk. This diagram shows the type states used in verification of a journalist messaging public key. We have a public key that's been sent over the internet. It has the role of journalist messaging, meaning it's intended to be used by a journalist for the purpose of encryption. And even if we think that this key has come from a system we trust, such as our own API, we want to make sure we've not been victim to an attack, such as a man-in-the-middle attack or an on-path attack. So before we do anything with this key, we need to verify that signature and expiry date are valid. If the checks are all okay, then it becomes verified and can now be used for cryptographic operations. If we want to serialize this key, for example to save it to disk, we must explicitly mark this type as unverified using the toUnverified function. From there, we can get access to our serialization functions again. This is not just used for single cryptographic keys though. For example, we use the approach to verify our entire key hierarchy. This is very similar to how TLS works on the web, where we retrieve an implicitly trusted anchor key from local secure storage, and then we use that to verify the entire hierarchy, which we'll fetch from the API. The final structure I'm going to talk about today is our signed form. This structure is used when a client application or service wishes to send some data to another service. Before the data can be actioned, we need to verify that the form was truly sent by the actor who claims to have sent it. The form has a type parameter that requires the type can be serialized and deserialized using the SERDI crate. They also provide a role type, which represents who has signed the form. This helps the verifying service look up the right key to use and helps our type system enforce that it's done correctly. Finally, we serialize the type T into a byte buffer and then sign this byte array in addition with other information such as creation and expiry timestamps. We sign exactly the bytes transmitted, which is good security practice and reduces risks when verifying the form compared to other more complicated approaches to signing structured data. To give a worked example of form verification, we can imagine with some kind of journalist status service. We first will start with a verified key hierarchy from before. This key hierarchy was pulled from the API and verified using a trust anchor. We now introduce a status update request from a journalist. The journalist used a HTTP post endpoint to send over a form containing the changes they'd like to make to their status. You can see here that the form is wrapping an update status struct and is signed using a key with the journalist identity role. We take the verified key hierarchy, which due to its verified status can be used for cryptographic operations. We combine the key hierarchy together with the form to verify and wrap this outer layer. This provides us with the raw update status form body, which can then be sent to the database. In summary, types give us superpowers. They allow us to encode the rules of our system in a way that can be checked compile time, helping prevent mistakes. All this is great, but types are not the end of the story. I'm going to hand off to Zeke to talk a little bit more about testing, metrics, and monitoring of our highly secure and anonymous system.
Hello everyone, I'm Zeke Hunter-Green, and I'm going to talk a bit about testing and observability for secure messaging. First, I'll go through a few testing techniques that we've found useful for this project. The first one is our use of test containers. Test containers is a library that lets you spin up Docker containers during integration tests, and in our case we spin up a Docker container per backend component of the system. So in CI, we will build Docker images for these 7 backend services and then spin up Docker containers for each. And that lets us run integration test scenarios like sending a message through the entire system from a source to a journalist, or having the cover node and journalists rotate their messaging keys, that kind of thing. And we found that very useful for testing the integration between all of these services. The next technique I'll talk about is time travel. So secure messaging involves a lot of time-dependent events. An example of that is a journalist creating an encryption key every day, and that encryption key needs to expire after 2 weeks. So in our integration tests, we want to be able to make assertions about the state of the system and sort of travel through time to make that assertion at different points in time. So the way that we achieve that is with this time machine, which boils down to 2 different implementations of a now function in a time module in our common library. So the implementation on top will be compiled if we are running tests, and that implementation just reads a fake timestamp out of a file. If we are not running tests, if we're in our production environment, then the implementation of this now function will return the current time kind of as you'd expect. So then the way we can use that is in a test like this. So this is an integration test that will create a journalist key or rotate a journalist messaging key. So the first few lines of this test create the journalist key and publish it to our API, passing in the current time. Then we can fetch all of the keys from the API and assert that our new key we've just created is in the response. Then we can call our time travel function, passing in the current time plus 14 days, and that time travel function is going to write that fake time to the file system in each of our test containers. Then after that, if we fetch the keys from the API one more time, the key we created at the beginning of the test will now be expired, so we can assert that that key is not in response from the API. Another testing technique is test vectors. So we want to test the integration between our back-end systems and the mobile apps. So the way that we do that is with test vectors. So we can add this macro call to save test vectors in the test we just went through. So after having created a key and published it to the API, we can call save test vectors. So this is a custom macro we've built, and that writes some state to the file system. That state will include the published keys, so that the response from the API, including all public keys. And that file we can check into version control. Then after having run the integration tests, we can run the mobile apps tests, which will read that state from the file system. So in that way, we're sort of testing the integration between all of the backend systems and the mobile apps using those test vectors. Next, I'll talk a bit about our approach to observability. So we use a metrics library to collect metrics, which we then send to Amazon CloudWatch, which is AWS's monitoring and observability service. And then from there, we send those metrics to Grafana to create graphs in a dashboard that our team looks at every day to make sure that the system is behaving the way we want it to. So the metrics library gives you this facade, which provides macros similar to the logging crate, which let you create metrics. And it is backend agnostic, so whether you're using CloudWatch or Prometheus or another metrics backend, most of the code to create metrics is going to look the same. So here's an example of creating a metric. So this is in the cover node in the bit of code that is pulling messages from Kinesis. So we can call metrics counter to create a new counter called u2j messages from Kinesis, and then increment that counter. It'll start at 0, and we can increment it by the number of messages we've just pulled from Kinesis. So this is a really nice little one-liner to create a new metric in the cover node. This is how we can send the metrics we've collected to CloudWatch. We use this library called metrics CloudWatch, and it's just a few lines of code that we see here in order to instantiate this backend. So first we grab some AWS config from environment variables, create a CloudWatch client, and then initialize metrics with metrics CloudWatch. We can namespace all of the metrics we're collecting in the API with the namespace API, and tell the backend to send metrics only every 60 seconds. We also use Axum Metrics, which is metrics middleware for Axum servers. So we have a few web servers in the system that are all Axum servers. And this is how we can add that middleware. So here we're creating a router for our API, and we can add a bunch of routes like the public keys endpoint and a few others, and then we can add a layer to this router and pass in the Axum metrics default metrics layer. So this is just a one-line change to our configuration for our Axum server that will give us metrics on total requests and the size and duration of requests and responses, and label all of those by endpoint, method, and response status code. So there's a lot of really useful information about this Axum server. And we can represent that information in a Grafana graph that looks like this. So it's API requests broken down by the status code, endpoint, and method of all of these requests. Like in any system, one of our goals in monitoring is to assure ourselves that the system is working the way it should be at any given time. And for secure messaging, one of the most important measures of that is delivery of messages from sources to journalists and from journalists back to sources. Secure messaging is opaque by design in certain ways. So that presents a sort of unique monitoring challenge. In order to keep sources anonymous to network observers, we don't want any information on the timing of real source messages to go to any third parties. So that includes AWS or Fastly, etc. And really, we don't want that information to leak anywhere outside of the on-premises cover node. And that means we can't add any tracing of real messages going through the system. So with that constraint, how can we monitor the system and make sure that it's behaving the way it's supposed to at any given time? Our solution to that problem was to create a tool that we call the Message Canary, which is a synthetic testing and monitoring tool which sends real messages through the system on a schedule. This is what the architecture of the Message Canary looks like. So the Message Canary is running on an EC2 instance in AWS. It's running in production constantly and sends a real encrypted user to journalist message once every hour. And then on the other side, we're also simulating a journalist receiving that real message. Whenever a message is received, we can create a metric with the duration of time that it took for the message to be delivered. And then we also send messages from journalists to users in the other direction. Whenever a message takes more than 3 hours to be delivered, we can create an alarm. So that gives us some graphs in Grafana that look like this. So on the top, we have the number of undelivered messages, and in both directions, that number is 0 during this 1 week period. And on the bottom, we have delivery times. So bottom left is the delivery time for user to journalist messages, which is all under an hour. And bottom right is journalist to user messages, also under an hour. To summarize our use of Rust, as Sam described, Rust's type system gave us some very strong compile time guarantees, and our use of the type state pattern for types representing cryptographic keys make it impossible to use the wrong kind of key in any given situation. Rust's mature ecosystem makes things like creating web servers, metrics, tracing, error handling, and testing really straightforward. And Cargo was very useful in this project. In addition to it as a build system and package manager, we used it as a workspace management, testing tool, formatter, and linter, and that was all very straightforward. Over to Daniel.
Thanks, Zeke. It's super exciting that secure messaging is finally live after having spent the last 3 years developing it. And from launch day, our backend has been handling more than 5 million cover messages per day. And we had a little silent rollout up to that took us a few weeks. And pleasingly, we didn't encounter any significant issues with the Rust services. They've been just deployed and ran and all was fine. The only tricky bits and bumps in the road were actually with the mobile apps, which were much harder also to observe, debug, and release. And while we cannot discuss any particular stories, I think we can overall say that we're quite pleased with what we've seen during the first weeks after launch in terms of quantity and quality of messages. And that makes us all really excited to continue working on the project. This project also has been unique in having started as an academic research project. It's quite rare that research makes it over into the real world where it has real world impact. And as part of this ongoing collaboration between the University of Cambridge and The Guardian, we also have published a white paper. And you can read that if you want to learn more about the protocol details, about the overall architecture, and for instance, the UX aspects that were quite important for the final product that we shipped. And in the same way, many insights also made their way back into the university curriculum. So for instance, Martin Kleppmann and I, we run a cryptography engineering course, and this now incorporates many of the ideas that you've just heard from them and Zeke about how to use types to increase misuse resistance of APIs. And this is because we think that it's really important that the next generation knows how to use the right tools effectively to write secure software and especially secure protocols. And finally, secure messaging is open source. It's available on GitHub. And we also have contact details for responsible disclosure if you find any security vulnerabilities. So this was already a long presentation, but there are so many other interesting aspects that we simply couldn't cover today. And one is, for instance, the journalist client, which is the software that the journalists use. And we implemented that using the Tori framework, which allowed us to reuse even more Rust across different components. There have been also a few interesting performance wins that were unlocked by Rust. For instance, when we migrated the appender from an edge service to a microservice running on a very small EC2 instance. And of course, we couldn't cover any of the cryptography or the actual protocol in any detail, but you will find them in the white paper. And with that, thank you very much for joining us today, even though we couldn't be there in person and you only see us on the screen. And a huge thank you to everyone who has been involved in the project, from the original cover-up researcher team to everyone at The Guardian who has contributed and supported secure messaging over the last 3 years. And we hope to see many of you in the Discord channel. Please ask any questions and let's continue these conversations. And with that, all the best from London, and thank you so much for your time.